All right, 37. So this section is called conditional probability. In the textbook, that's what they would call it. But the main distinction we want to make today, okay, under this section is we want to talk about dependent events versus independent events. And in particular, obviously I want to show you the difference between them, but we're going to spend a bit more time now on dependent events, where something happens beforehand and affects our current probability. For example, I'll give you one example. Would it matter me studying for a test? Would me studying for a test affect how I do on a test? It would, right? Most of you would say yes. Some of you are like, no, I never study, but it would, okay? So those would be dependent events. I would actually have to consider that. Me wearing a green shirt and doing well on the test, are those dependent events? Not really. Some of you might differ. You would say, no, I totally believe when the color changes the outcome. But really it doesn't, right? So they're independent. They have nothing to do with each other. Okay, so that's the idea here. If two events happen either simultaneously or in sequence, and it does not affect the total number of possible outcomes, we call the events independent. So it could happen at the same time or in sequence, but it doesn't affect the total possible outcomes. We call those events independent. So let's do this example here, and I use tree diagrams to do this one. Actually, tree diagrams are very popular in probability, especially when it's this type of question. What is the probability of rolling a 5 and rolling a 3 with two 6-sided dice? Okay. This will be my first event here, is roll a 5 with die 1. Okay, die number 1. This is my first event. Okay, so me rolling a 5 is going to come here because it's probability, and there's always a chance that I don't roll a 5, correct? That's how probability is always, it's happening, it's not happening. So the probability of rolling a 5 is 1 over 6, correct? Me not rolling a 5 is 5 over 6. So these add up to 100%, right? So that's fine. My next outcome, the desired outcome, is rolling a 3. So rolling a 3, and this represents die number 2. It's almost like my second event. Okay. So basically we're running out. So let's say you get a 5, but then on the second, there's still two options for that second event. So rolling a 3, and this would be not rolling a 3. So the rolling a 3 is 1 over 6. Not rolling a 3, 5 over 6. Coming down to this one, there's either rolling a 3 and not rolling a 3. Rolling a 3 is still 1 over 6, and this is 5 over 6. So I don't know if you noticed, this is what I want to highlight in this scenario. Do you notice that the total number of outcomes stays the same? It's always out of 6, right, in this tree diagram, no matter where we go. So pay attention to that. Now, if I ask you to state the outcomes, this would be probability of rolling a 5 and rolling a 3. Whoa, you're mixing up chapter 3? Yeah, that's what we're doing. That would be 1/6 times 1/6. That's how you would find the probability. Okay. Then we have probability of rolling a 5. So I'm going down this branch and then down here, and not rolling a 3. That would be what? 1/6, right? Times 5 over 6. Then the other option is not rolling a 5, but rolling a 3. That's 5 over 6 times 1 over 6. And then you come down, way down here is probability of not rolling a 5 and also not rolling a 3. So that's 5 over 6 times 5 over 6. You may want to turn it into a decimal if you want, but you don't have to. So if you go 1 times 1, that's just 1. 6 times 6 is 36. Second outcome here, where we roll a 5 first and not roll a 3 second, that would be 1 times 5 is just 5. 6 times 6 is 36. Same with this part right here. 5 over 36. The last one is 5 times 5 is 25. 6 times 6 is 36. Let's do a quick check here, because if you don't, you made a mistake. Let's add up, because they're all out of 36. Let's add up all the numerators. 1 and 5 is 6, plus another 5 is 11, plus 25 is 36. So you're just doing a little check here. You're realizing that you have 100% here. All your outcomes should always add up to 100% here. Okay? So this is a tree diagram with where nothing changes, right? The first event does not affect the second event. Regardless if you get a 5 or you don't get a 5, it's 1 out of 6, 5 out of 6. It's still 1 over 6 and 5 over 6. Like rolling the 3 has not been affected by what happened before. Crickets, crickets. Just wait for me till I get to the dependent, then we'll see it. So these are independent events. I will make a note here. Sorry, this is sideways. I know it's a little bit. But rolling a 5 or not a 5 did not affect the second outcome. Sorry, I'm going to put it so you can actually read it. Okay. So rolling a 5 or not rolling a 5, okay, did not affect the second outcome at all. And if you don't see it now, let's just do another one and you'll see it. Okay. Let's go to page 38 and let's look at dependent events. When are you dependent? I'm going to go orange because that's what I used for the first page there. If the first event affects the second event and so forth, we can say that the events are dependent. Consider a deck of cards. Geraldine draws one card and does not replace it, then draws another card. What's the probability of drawing an ace and then a face? So we want an ace card and then a face. Okay, how's that going to change things? So first event is ace, trying to get an ace. Okay, that's my first event. Second event is trying to get a face. Okay. So every time, guys, when it comes to probability, you're going to go getting an ace or not getting an ace. That is the question. Right? What's the probability of getting an ace with a standard deck of cards? Okay, you are awake. Okay, good. 4 out of 52, right? So what is it of not getting an ace? 48 out of 52. All right. Good. And what's my second? What do I want? Secondly, I want to figure out the probability of a face or not a face. Face, no face. Okay, question. What is the probability of drawing a face after this happened? Is it going to be out of 52 or is it going to be out of 51? 51, because what? It has not been replaced. The first card, like a card has been removed, not replaced, so it's now out of 51. Immediately you can tell, okay, things have changed. So what is the probability of getting a face if an ace has been removed? Guys, pay attention, pay attention. This ace affected the total, correct? But how many faces do I still have? 12. All right. Let's go back. So what would it be of not getting a face here? This is still 51. It would be 39. Yes. How do I come up with the 39? Right. 51, subtract the 12, so this is 39. Okay. What about here? I'm not getting an ace. What's the probability of getting a face here? You grabbed something other than an ace. Okay, that's what this is saying. Well, I still have 51. For both of these, because things have not been replaced, I still am down to 51. Okay? I still have 12 face cards. And I still have 39 non-face cards, right, left here. So let's do the probabilities here. Probability of ace and face. Probability of ace and not grabbing a face. Probability of not grabbing an ace and face. These are considering all possible outcomes here. Probability of neither one. No ace, no face. So here you have to go 4 over 52 times 12 over 51. 4 over 52 times 39 over 51. 48 over 52 times 12 over 51. 48 over 52 times 39 over 51. Make sure you write this down. Okay. And because of time, I'm just going to, once you figure out what 52 times 51 is, which is 2652, just write it down for every single one. That's going to be your answer in the denominator. 4 times 12 is 48. 4 times 39 is 156. 48 times 12 is 576. And this is 48 times 39 is 1872. So here you have the outcomes listed with their probabilities. Hold on. I already turned this into a decimal. I turned this one is 181%. This one is 5.88%. This one is 21.72%. And the last one is 70.59%. Because you're wondering, every time I just divided them, right? I went 1872 divided by 2652, and I multiply that by 100 to give me that percentage. I already checked. If you add this up, you get 100%. Okay, so that's always a check you want to perform to make sure you got this right. Your tree diagram is indeed correct. This has to add up to 100%. Or if you just added up all the numerators, you would have come up with 2652. Then you also know you're right. So I want you to highlight this part. The fact that you ended up with less here, it changed. What happened before changed the outcome, right? Total changed. Therefore, dependent events. That's basically the main idea before we continue here is I want you to see that things have changed. Okay? So these are all possible outcomes. Okay? This is a little bit, this is like, wow, this is a lot, right? Hold on. I could have just asked you, based on this question, what's the probability of drawing an ace and a face, right? You would have known, it's like, oh, well, I have 4 out of 52 at first, but then one is removed and not replaced. How many aces, how many faces do I have? 12, but now it's going to be out of 51. So literally, if I asked you what's the probability of an ace and a face, you would have just, if you answered that, you would have been fine. Okay? I could have asked you what's the probability of getting an ace and not a face, then you could have just shown me this part right here, right? It's 4 out of 52 aces, and then I have 39 out of 51 that are, because the 51 is now down 1 because of the 52, removing a card, you're down to 51. This is all you would have to show me and just come up with a 156 over 2652, okay? But I'm showing you all possible outcomes, and that's what the tree diagram is really good at, showing you this. But this is what where things are going to change, and I want this on your study sheet. Under dependent events, you're going to have this boxed in formula right here. But I only want you to have one here. So not the or, cut it off there. I just want you to have this one on your study sheet, and you're going to have dependent over it. And here's some notation, some annoying notation facts, okay? I want to zoom into that. Watch what this is saying here. It's saying the probability of A and B happening, okay, is equal to probability of A, go ahead, times, what is this saying right here? Listen carefully. This is saying probability of B given that A happened beforehand. That's what this notation is saying, okay? So, and I do clarify that here. The probability of event A and event B happening is equal to probability of A times the probability of B, given that A already happened. That's what this little thing is saying right here. When you see that, this is kind of indicating that this is a dependent probability scenario. You haven't seen that before, okay? So it's okay to be a little bit worried about seeing that, but I just want you to have that on your study sheet. All the way up until now, we did this. I want you to go to 37 with me. Go to 37. That formula, I skipped it at first, but now we're going to look at it again, okay? If it is independent, then this is, I just want you to have this one right here, not the or. We don't need two versions of it. They're both saying the same thing. So you're going to have independent on your study sheet and saying the probability of A and B happening is probability of A times probability of B. That's it. They don't affect each other, right? What happens first doesn't affect the second one. Can I just say this keyword? Nothing has been removed. Okay. Another keyword would be items are replaced. That's another one. So if you play a card game and they mention that you draw a card, you get an ace, but then you put it back in the deck, you are not looking at dependent events anymore. Does that make sense, guys? You put it back, it's not dependent, so don't fall for it, okay? If oh, my snack bin, I didn't give you snacks, right? Okay, that's a good one. If I walk around with these snacks and somebody grabs one, this is a made good bar. There used to be, let's say there's 12 in here. Someone grabs it and eats it. The probability of somebody else getting a good bar is, it's gone down by 1, right? Somebody ate it. So those would be dependent events. So I'm not going to eat it, don't worry. I'll give it to you. I'll put it over there later. But if it's dependent, we use this weird notation right here. Not probability A and B like it used to be. But now we have this bar, this vertical bar saying probability of B given that A has happened. Okay, this is an indication that something has happened and has affected this one. Maybe I'll just go into more examples and then we'll figure it out from there. Let's keep going. 30, we're going to go to 39. It's not all about tree diagrams, guys. It's not all about tree diagrams, but sometimes we have it. Okay, there are 3 green, 2 red, and 4 blue marbles in a bag. You're drawing 2 of them in a row. Notice that. 2 of them in a row. Determine the probability, and I want you to answer with and without replacement. Okay? We're going to say this. We're going to cross out the with. Get rid of that. Just say without replacement. We're just going to turn this into a dependent situation. Okay? So I'll do 1 here with you. It's asking us the probability of picking a green and a red marble without replacing. So dependent events, right? So probability of G and red is going to be, I'm going to be annoying with the notation a little bit, okay? That's going to be equal to probability of G times probability of R, correct? Can I just leave it like that? No, I got to go with this annoying notation. I have to look it up every time. I forget, okay? Vertical bar, and you're going to put G there. So this is saying probability of red given that G happened. And now we do the math. What's probability of green? How many do we have total here? 9, right? So I'm going to put 9 here. So we're going to go 9 here. We've got 3 green. So we're going to leave it like that. We could reduce it. And what's the probability of red? It's 2, right? But what goes down here? How many? You used to have 9, but we're now replacing it. So we're down to 8. Okay? Not replaced. Green one. The green one has not been replaced, so we're going from 9 to 8. That's why you have to use this notation. I'm not going to make you use the notation, but I can see the province saying, what's wrong with the notation? You know, Jamie, there's no Jamie in here, right? No. Okay. Jamie is solving this and is using this formula to solve this question. Is that correct? And you'd be like, no, it's not correct because Jamie's assuming these are independent events. we should use this. Maybe they'll do a multiple choice. I don't know what they're going to do. But don't worry about it too much. I won't make you use it necessarily, but just be aware of it. This is just saying, hey, something has changed. That's all. 3 times 2 is 6. 9 times 8 is 72. And that is, let's just get our decimal out of that. 0.0833, which turns out to be 8.33% of these two being happening at the same time or in sequence, right? How would this change? I will just do one. If, is this marbles? Yeah. If marbles are replaced, let's just do one here. I wanted you to do the whole page, but it's going to get too tedious and too busy. If marbles are replaced, then P of G and R is just going to be PG times PR. That's it. Because it's nothing is affecting the other one. Okay? So we would go PG is 3 over 9. And what's the other one? 2 over 9. That's 6 over 81. And I'll just leave it at that. So this is independent. This would be independent. This is dependent. Okay? So just so you see the difference, here nothing has affected the total. Okay? Can I ask you to try B to D? Figure out the probabilities. E, you might want to wait for me for E. E is very important for you to know how to do it because it's a bit of a classic. But can you try B to D? I think you need to take a break from my voice here. It's hurting your ear time, but I think I'll just make sure you know if it's two blues, probability of blue and blue. Okay? So it's probability of blue times probability of blue given that blue happened. A blue was drawn. Okay? That's kind of what we want to go by. We understand this is, how do we know this is dependent, guys? How do we know? What's the key word? It's this one right here. I should have highlighted that. This is a dead giveaway that this is dependent. That is the dead giveaway. Like it's, oftentimes that is what it is. Like that things are being removed and not replaced. Okay? And obviously that's going to affect the outcome. So we've got probability of blue. We've got, let me just look 4 out of 9. And then it's 3 out of 8. How so? Well, the 8, I think most of you know, right? It went down by 1. But the blues has also been affected. The number of blues has gone down by 1. Okay? So in this case, it would be 12 over 72. I'll just leave it at that. Does that make sense? That both numbers are affected in this case? Okay. Blue and green. So I'm not going to do the notation in this case. I'm just going to go with blue. We've got 4 out of 9. And 1 has been removed, so it's 8. So we'll just grab the 3 greens. So this is 12 over 72 as well. Is that right? Yeah, it is. Okay, good. 2 green marbles, green and green. So we have 3 over 9 to start, and then it's 2 over 8. My next one, so that's 6 over 72. And here's the classic. This one, I honestly, I would say put this on your study sheet. 2 like-colored marbles, star, star. What does that mean? Anybody know what is going to happen here? What should we consider if it's like-colored marbles? You've got 3 different colors, right? So it could be, this is cases. That's why I want you to have that on your study sheet. We could have green, green, or red, red, or blue, blue. Okay? So you kind of have to consider all 3 cases. Green, green, we already did that up here. I'm just going to show you here. 3 over 9, 2 over 8, plus red, red, we haven't done that one, so we'll just quickly do it. 2 over 9, and then we're down to 8, and we only have 1 red left. Plus blue, blue, I think we did that up here. 4 over 9 times 3 over 8, right? It goes down by 1 in the total. It goes down by 1 when it comes to the blues. Okay? That ends up being, let me just get my act together here. This one is green, green is 6 over 72. Yeah, plus 2 over 72 plus 12 over 72, sorry, not 27. And so if you add that all up, because the denominators are all the same, you can just go 6 and 2 is 8 plus 12 is 20. Okay, that ends up being 0.2778 if you want to have it as a decimal, or 27.78%. So this one here, I would definitely say have these cases. The province has done light colored chocolates, or like they do that a lot, this one. And it's worth 2 marks, by the way. I don't know why, but they always make it worth 2 marks. So right away, if you see that, you're like, oh, there's more than meets the eye, okay? All right, I'm going to stop here today, but please try the pages that follow. I'm going to say for today, for the weekend, 40 and 42. Okay? I will post whatever is on 41 as well. If you get stuck on 41, listen carefully. If you get stuck on 41, I am using if you get stuck on 41, you're using this formula and working backwards. So maybe, I thought you were going to stop, Mr. Dirksen. I thought so too. Let's go to 41 just in case. A jar containing black and white marbles. 2 marbles are chosen without replacement. What does that tell you? Dependent. The probability of selecting a black marble and then a white marble is 0.34. The probability of selecting a black marble first on the first draw is 0.47. What is the probability of selecting a white marble on the second draw given that the first marble drawn was black? Does this mean anything to you? It's a long sentence. How could we write this in just using simple notation? It's asking for this. What's the probability of getting a white marble given that the first one was black? It's asking you for this. So you just have to use your formula, okay? What is the formula in this case? Please don't use this one. This is just a variation. I'm just going to show you how to use it, use the original. You want to use this as your model. This is the one that you will have on your study sheet. Okay? So they're literally asking you for this part right here. What is that? That you can replace that with X if you want. Okay? Do we know this one? Probability of A and B? It's right here. The probability of selecting a black marble and then a white marble is 0.34. So we're going to go 0.34 there. Probability of selecting a black on the first draw is 0.47. And we're going to say this is what they're asking us for. I don't know why I selected a bracket there. It's just this. So this is your X. This is your unknown. What would you do to both sides to get rid of, you got to get rid of this. So you basically divide both sides by 0.47. I'm just going to say this. This page you will do last, okay? I don't want you to spend too much time on this over the weekend. But please do a few of those other pages that I assigned just now. So when you divide that, you get 0.7234. So P is 0.7234, or 72.34%. I haven't seen these, to be honest, on the exam, but if they do, I think what I would want you to, I would expect you to see is, as soon as you see this drawing a white marble, given that something else happened, you're like, cling, I'm in the dependent probability mode. I'm going to use this formula to help me out. Okay? All right, 41 to 42, that's your homework. That's it. Try a few, and then we're going to continue conditional on Monday.